Let's look at another application of differential equations. We are going to solve a mixing problem. So we have here a tank that has a volume of 1,000 liters and 10 kilograms of salt have been dissolved into this 1,000 liters of water. And we have brine, or a salt solution, that is flowing into the tank. The concentration of the brine is 0.05 kilograms of salt per liter, and that enters the tank at a rate of 5 liters per minute. So we have a solution being poured into the tank, and the tank already has some solution of salt in it. This solution in the tank is thoroughly mixed, and it drains from the tank at the same rate. We want to know how much salt is in the tank after t minutes. So let's try to draw a little picture here so we can imagine what's going on. We have some tank, whatever shape it is, we don't care. But we have some tank, and it has some solution of salt in it. So there's some water in here that's got some concentration of salt. And flowing into the tank, we have a higher concentration of salt. So we have liquid flowing into the tank that's more salty, and at the same time that the liquid is flowing in, we have a drain maybe on the other side where the solution is pouring out. So gradually over time, as a more salty solution flows into the tank itself is going to have a higher and higher concentration of salt. We would like to know, at time t, how much salt is in the tank. So we will set up a differential equation that describes this mixing problem, and we'll solve it to find a function describing how much salt is in the tank after t minutes. So let's first fix some notation. For example 7, let's let S of t, let's let this be the amount of salt in the tank at time t. And ultimately, this is what we're trying to solve. Something that will be really helpful here is to keep track of units. So the units for the amount of salt in the tank, well, these are units of kilograms. So we're going to measure this in kilograms. Now, we have some information about rates here. We have an information that this solution that's a little bit saltier is entering the tank at a rate of 5 liters per minute. And we're going to look at the rate of change of the amount of salt in the tank. So let's think about S prime of t, or let's just call this ds dt. This is the rate of change of salt in the tank. So we've got a certain solution of salt, but a saltier solution is flowing in. And so eventually the solution inside the tank will get more and more salty. And hopefully we won't get more and more salty as we solve the problem, because it will be admittedly a rather long problem, but stick with it. It's really cool how we can apply differential equations in a situation like this. So what are the units for the derivative here? The rate of change of salt in the tank. Well, salt is measured in kilograms, and time here is being measured in minutes. So kilograms per minute, that's the unit for the derivative of S. We want to write a differential equation that describes this rate. And we want to do that using the information that's given here in the problem. We can think of the rate of change of salt as the rate of salt flowing in minus the rate of salt flowing out. So I'm going to write this as the rate of salt flowing in minus the rate of salt flowing out. Now let's work on getting an expression for these two pieces of information here. Let's first think about the rate flowing in. So the rate flowing into the tank, well, we have a concentration of 0.05 kilograms per liter, and it's flowing in at 5 liters per minute. So let's look first at the 0.5 kilograms per liter, and this is a constant concentration that's flowing in. The concentration of the salt flowing in does not change. The concentration of the salt flowing out, that will change. That will change because the tank's getting saltier. But the salt that's flowing in, or the brine, that concentration does not change. So the rate of change of salt that's flowing in, that will be using the brine here that's flowing in. So the brine has a concentration of 0.05 kilograms per liter. And if we multiply the concentration of this solution by the rate at which that solution enters the tank, notice how the units work out. Let's multiply by 5 liters per minute. That's how fast the solution is flowing in. Notice that the liters here cancel, and we have units left over of kilograms per minute. Those are the units we want for the derivative. So 0.5 times 5, that is the expression for how fast the salt is flowing in. So that's the rate of salt flowing in, just thinking here of the brine that's flowing into the tank. So the rate of salt flowing in, this is 0.05 times 5. Once again, the units here are kilograms per minute. Now let's think of the rate of the salt flowing out. So for the rate of the salt flowing out, we're going to do a similar sort of a thing. We're going to think of the concentration of the salt flowing out, and then we'll multiply by 5 because the rate that the solution drains is the same as the rate that it enters. So I can express the rate that the salt flows out as the current concentration. So let's write this as current concentration in the tank times the rate at which it's flowing out, times the 5 liters per minute. Now the units for the current concentration in the tank, that will be kilograms per liters. So our units are going to work out again here. We multiply kilograms per liters times liters per minute, and we're going to get kilograms per minute. Now, what is the current concentration in the tank? Well, that's just the current amount of salt divided by the volume of the tank. So we can express the current concentration in the tank as S divided by 1,000. So the current concentration here, that is the current mass of salt divided by the volume of the tank. And then we multiply by the 5 liters per minute. So once again, let's keep track of the units to see how this is working out. The S of T, this is mass, that's kilograms. So we have kilograms per liter times liter per minute. The liters will cancel, and all the units here are going to be kilograms per minute. So this is the rate at which the salt is exiting the tank. That's how many kilograms per minute of salt are leaving the tank. So this is the rate of salt flowing out. Now we can write this as S divided by 1,000 times 5. We can simplify a little bit here. 5 times 0.05 is 0.25. And then the 5 divided by 1,000, this simplifies to be 1 over 200. So we can write this second term as S divided by 200. And this equals ds dt. Now, admittedly, this was quite a bit of thinking to get here. This is probably rather confusing. So I'd encourage you to rewind, watch this again, and make sure that it makes sense how we're getting this expression here. One thing that really helps me to think through these problems is to focus on the units and make sure when I'm simplifying these expressions, the units always work out to exactly what I need them to be. So this differential equation describes the rate at which the salt is leaving the tank in units of kilograms per minute. If we can solve this differential equation, and we can, then we will have an expression for the exact amount of salt in the tank at any time t. So now our focus is to solve this differential equation. Now notice that this differential equation isn't actually all that terrible. The problem at hand might be kind of complicated, but we actually get a fairly simple differential equation. This reminds me of volume and work problems where we had a rather difficult setup, but once we got to the actual integral, it turned out to be a rather simple sort of integral to evaluate. So let's work on evaluating this differential equation. First thing I'm going to do is to get common denominators between these terms here. The 0.25 is just constant, but I want to get a common denominator here so I can add these. So I'm going to multiply the 0.25 by 200 divided by 200. That will get me common denominators of 200. And 0.25 times 200, well, 0.25 is the same as a quarter. So what's 1/4 of 200? That is 50. So I can write this as ds dt equals 50, that's 200 times 0.25, minus s divided by 200. Now let's solve this differential equation. It's separable. In fact, it's also autonomous. So we're going to divide both sides by the 50 minus s, move the dt to the other side, and work through the solution. So 1 over 50 minus s ds equals 1 over 200, which is just constant, dt. Now we can integrate. So for the integral in terms of s, this is going to use natural log. So we have natural log of the absolute value, 50 minus s. And then I need a negative out front because if I took the derivative using chain rule, I would multiply by the derivative of negative s, which is -1. So here's the correct antiderivative for this integral. Now we want to find the antiderivative of 1 over 200. Well, that's simply 1 over 200t. So 1 over 200t plus an arbitrary constant. I'm going to multiply both sides by negative here, and multiply the negative times this arbitrary constant just gives us another arbitrary constant. So we can write this as natural log absolute value of 50 minus s equals negative t over 200 plus c. Now we want to solve for s. So I'm going to raise e to the power of both sides, and then we have this progression where this turns into e to the negative t over 200 times e to the c, so we'll just write a c out front, and we'll deal with the absolute value bars here by making sure that this c can be arbitrary, positive or negative or 0. So once again, this is a similar concept to what we saw in example 1b. So we have 50 minus s equals c e to the negative t over 200. I still want to solve for s, so I'm going to go ahead and subtract 50 from both sides. I have negative s equals c e to the negative t over 200 minus 50. And finally, I can multiply both sides by negative 1, and I have s equals c e to the negative t over 200 plus 50. Distribute the negative 1 to both these terms here. Now, negative 1 times c, well, c is just an arbitrary constant. So the c here is actually different, but since c is just an arbitrary constant, instead of writing negative c here, I'm just going to write an arbitrary constant c. And at this point, we have the general solution to the differential equation. So what we can do now is find the particular solution by using one more piece of information. There's one piece of information in the problem that we haven't seen yet. Let's see if we can find what that is. It's this right here. Initially, here is the amount of salt in the tank. S of 0, the amount of salt at time 0, is 10. So we can use that fact to solve for our arbitrary constant in the general solution. So let's do this off to the side a little bit. We're told that the initial amount of salt in the tank is 10 kilograms. So this is equal to when we plug in 0 for t. If we plug in 0 for t, notice that we have c times e to the 0. E to the 0 is just 1. So if we plug in 0 for t, we're just going to be left with c. So we have c times 1 plus 50. Solve for c, and we get c equals 10 minus 50, negative 40. So here is the answer. The amount of salt in the tank at any time t is negative 40 times e to the negative t over 200 plus 50. This function describes exactly how much salt is in the tank at any time t. So we found how much salt is in the tank at any time t after t minutes. Now we want to know how much salt is in the tank after 1 hour. In order to find that, we're just going to plug in 60 minutes here, since time is measured in 60. So the amount of salt at 1 hour is S of 60. So S of 60, we'll plug in 60 for t, and we get negative 40 e to the negative 60 over 200 plus 50. We can go ahead and throw that into Mathematica, and we get a value of approximately 20.4. This is measured in kilograms. Now, does this make sense? Does it make sense that we have 20.4 kilograms after an hour? Well, let's look at the problem again. Initially, we had 10 kilograms of salt, and after an hour, we said we have 20.4. So the amount of salt in the tank is going up. But this makes sense because the concentration that's flowing into the tank has a higher salt content than the content of the salt that's already in the tank. So because we have a higher concentration flowing in, we would expect the amount of salt to increase. So initially we started with 10 kilograms of salt. After an hour, we have over 20 kilograms of salt. And we could find how many kilograms of salt are in the tank at any time using this equation here. If we wanted to know at what time do we have 30 kilograms, we could just set this equal to 30, solve for t, and we would be able to figure out exactly what time we have precisely 30 kilograms of salt in the tank. So even though this was a rather long and tedious problem, I hope you can appreciate how applicable differential equations is for this sort of an example. Let's take a look at one more application of differential equations. Check out the snowplow problem. And actually, spoiler alert, this problem doesn't even require separation of variables. So it doesn't even need to really fit in this section, but since we've been modeling some problems using differential equations, I thought it'd be a good idea to try this problem out. It begins snowing sometime before midnight and continues snowing at a constant rate. Right at midnight, a snowplow starts plowing. The snowplow plows at a speed that is inversely proportional to the current depth of snow on the road. At 1 a.m. after 1 hour, the plow has traveled 50 miles. At 2 a.m., the snowplow has traveled 30 more miles for a total of 80 miles. And here's what we want to find. What time did it start snowing? This seems like one of those ridiculous problem statements that are impossible, and we almost laugh just reading this. What time did it start snowing based on this information? But we can figure it out using differential equations, and it's a really cool problem. We have to be pretty careful how we set it up, so let me show you the procedure here. First of all, we have to fix our time variable very carefully. So we have to determine what the starting time is. What is time 0? So I think the best way to solve this is to let time 0 be the time that it starts to snow. So t equals 0. This is the time that the snow starts. And then later on, so this is sometime before midnight, later on, right at midnight, is when the snowplow starts. So let's call this t sub p. T sub p, this is greater than 0 now. We don't know what this time is, but this is the time that the snowplow starts. Well, I guess in some sense we do know what t sub p is. This is midnight, but we don't know what t sub p is in relation to time 0. Time 0 is when it started to snow, and sometime later is when midnight is, and we don't know what that time value is that corresponds to midnight. So t sub p, this is when the snowplow starts. And this once again is 12 a.m. But t sub p is not equal to 12 because we're measuring time based off of when the snow started. So notice that what we're actually trying to solve in this problem is t sub p. T sub p is the time after it started snowing to midnight. So if we can find t sub p, we'll backtrack to find time equals 0 when the snow started. We'll subtract t sub p from midnight. That will give us the time that it started snowing. So if we can solve t sub p, then we've solved the problem. Now let's define a couple of functions here. Let's say s of t is the depth of snow at time t. And then let's say that x of t is the distance that the snowplow has traveled. So x of t is the distance that the plow has traveled at time t. Now let's use the information that's given here to write down some conditions for these different functions. Here are some conditions that are satisfied by these functions. We know that at the starting point, at time t equals 0, there's no snow on the road. That's what we're told to assume. So at time t equals 0, the depth of snow is also 0. So we know that s of 0 is 0. We also know that the distance that the snowplow has traveled at time t sub p is 0. So time t sub p, that's when the plow starts. So the distance that it's traveled at that time is 0. We're also told at 1 a.m. how far the plow has traveled. 1 a.m. is 1 hour more than t sub p. So we can say the distance at midnight plus 1, that's 1 a.m. That distance is 50 miles. And there's one more piece of information that we can write down here. At 2 a.m., the snowplow has traveled 30 more miles for a total of 80. So we can write x of t sub p plus 2, this is 2 a.m., this equals 80, 50 plus 30. Let's take a look at what other information we're given the problem statement. We're told that the snow falls at a constant rate. So the rate here, that's the derivative of s. The rate of change of the depth, that's the rate at which snow is falling, that derivative is constant. So we can say here that s prime of t is some constant. And let's just call this constant r, some rate at which the snow is falling. So this expression here says that the snow falls at a constant rate. We're also told that the speed of the plow is inversely proportional to the depth of snow on the road. Now the speed of the plow is the rate of change of distance. That's x prime of t. So x prime of t is inversely proportional to the depth of snow. Inversely proportional means that we divide by the depth of snow. So we have some constant of proportionality, we'll just call it k, divided by the current depth of snow, which is s of t. Now using this piece of information, that the snow falls at a constant rate, we can find the function that describes the amount of snow on the ground. So take this function here for the rate at which the snow falls. If the rate is constant, then we can integrate to find the antiderivative of the rate, which is just the depth. So we can say that s of t is the antiderivative of this constant r. The antiderivative of a constant is just the constant times t plus some constant c. So if we know that the rate of change of the snow is constant, then we can just write the amount of snow as the rate times whatever the time is. And let's solve for this constant c now. We're going to use this little piece of information here. The amount of snow, or the depth of snow at time 0, is 0 inches. So S of 0 equals 0, but we could also write, if we plug in 0 for t, r times 0 plus c. Well, r times 0 is just 0, so this just turns out to be 0, and we have c equals 0. So the value of this constant, c, is 0. So this tells us that the s function for the amount of snow on the road is just r times t. We can use this and plug it into the derivative for x. So x prime of t, once again, that's the speed that the plow travels. X prime of t is inversely proportional to the current depth of snow, and we just found the function that describes the current depth of snow. It's some constant rate times time. So we can write the derivative of x as k divided by s, which is r times t. And I think it'll be more helpful here to write this as k over r times 1 over t. T is a variable. This changes. This is time. K and r are both constants. So what we see here, this looks kind of confusing, but k and r, these are just constants in the context of this problem. So we have an expression for the rate of change of the distance of the plow, or the speed at which the plow travels. We can say that dx dt equals some constant k over r times 1 over t. Now how can we find x from this piece of information? Well, we could do separation of variables, I guess. We could move the dt to the other side. Separation of variables isn't actually necessary here because the derivative is just a function of the independent variable. So to find x, we just simply integrate with respect to t. So I guess we could think of doing a separation of variables here, multiply dt by both sides. And now we can integrate. So the integral of dx, that's just the integral of 1, that's x, so there's our function x. And now k over r is a constant. So we have k over r times the antiderivative of 1 over t. The antiderivative of 1 over t is the natural log of t. We add plus some arbitrary constant. We'll just use c again. And here is a function that describes the distance that the snowplow has traveled in terms of time. Now I can solve for the value of this constant c by using this little piece of information here. This is an initial condition for this differential equation. If I plug in t sub p for time, then the distance, well, that's by definition when the snowplow started, so the distance is 0. So I'm going to plug in x of t sub p. This equals k over r times the natural log of t sub p plus c. And this distance at the very start that the snowplow starts, that distance is 0. So this tells us that the constant c is, well, if we solve for c here, we just subtract this expression from both sides. So c equals negative k over r times the natural log t sub p. Now at this point, it probably seems like we're sort of on a wild goose chase. What are we even doing here? We're trying to solve eventually for the time when the plow started, because that's the amount of time after it started snowing. So if we can find the value of t sub p, that will tell us how long it's been since the snow starts, and then we'll know when the snow started. And eventually we'll get there, but it might seem a little bit unclear right now how we'll get there. So just hang in there, and eventually we'll see the value for t sub p and have the end solution to the problem. So back to this function for x. This is the distance that the snowplow has traveled. We just found the arbitrary constant c, so we can go ahead and plug that in. So we have k over r times the natural log of t plus c, which is minus k over r times the natural log t sub p. I can simplify this a little bit. I can factor out the k over r. So I can write this as k over r times the natural log of t is the variable, minus natural log of t sub p. T sub p is ultimately what I'm trying to solve for. Now there's a rule for logarithms, which states that when you take the difference of two logarithms, you can write this as the log of the first argument divided by the log of the second. So I can write this a little bit nicer as k over r times the natural log of t divided by t sub p. That's just using a log rule to take care of the subtraction of the logs and to turn it as the log of a fraction. So this right here, this is our function for x. let's write that over here. X of t equals k over r times the natural log of t divided by t sub p. How can we use this? How does this help us solve the problem? Well, here are two pieces of information that we have not yet used. This tells us the distance that the snowplow has traveled after 1 hour and then after 2 hours. So I'm going to plug in these values for t into this equation, and I'm going to get two equations that will allow us to cancel out these random constant values, and we'll be able to solve for t sub p. Here we go. For the first one, I'm going to take this expression here and think about plugging in t sub p plus 1 in for t. So x of t sub p plus 1 is k over r times the natural log t sub p plus 1 divided by t sub p. And then use the second expression here. X of t sub p plus 2 equals k over r times the natural log t sub p plus 2 divided by p, t sub p. Now this first one, x of t sub p plus 1, that equals 50. So we can say that this is 50. And the second one, x of t sub p plus 2, this equals 80. So here we have 80. Now take a look at this. These two equations right here. The variable is t, time. We don't have the variable t anymore because we've been plugging in specific values. We do have the k and the r, and then the t sub p. T sub p is really what we're looking for. Now imagine taking these two equations and dividing one by the other. If we divide one by the other, then these constants will cancel out, and we'll have an equation where the only unknown is this expression for t sub p. So let's write that down here. Taking the fraction of these two equations, dividing one by the other, these constants would cancel out in the fraction, and we're left with the following equation. Natural log of t sub p plus 1 divided by t sub p divided by natural log of t sub p plus 2 divided by t sub p. This all equals 50 over 80. Here I have an equation where the only unknown is t sub p, so I can solve this. If I plug this into Mathematica and solve for t sub p, Mathematica tells me that the answer for t sub p is approximately 1.086. That's the value of t sub p. So what did we find here? After all this work, this is the time after it started snowing that the snowplow started, and the snowplow started at midnight. So about 1.08 hours before midnight is when it started to snow. And if we turn that into minutes, this is approximately 65.17 minutes. We're counting down minutes from midnight, so this would say at approximately 10:55 p.m. is when the snow started. Now, this problem probably felt rather laborious and a little bit confusing why we worked through it like we did. But I hope that you can appreciate the power of differential equations and just the sorts of problems that we're able to solve using this amazing tool.